So, good afternoon, everybody. Welcome to this webinar, and thank you for joining us. And thanks to SuperGen for putting on this event. I'm Saul Young, the Operations Manager at the Marine Energy Test Area, or META, and I'll be one of your speakers today, alongside um, Arnie Vogler from Catapult, and lead engineer for their MEECE team based in Wales. This webinar will showcase some of the at-sea testing that has happened at Meta and in Wales over the last few years. And we're going to look at some of the lessons learned, some of the benefits and challenges of at-sea testing, and maybe touch on some opportunities for future collaboration as well. So I'll get my slides ready, but yeah, thank you very much everyone for your time today and your participation in this session. If you've got any questions, please feel free to put them in the chat. There's going to be two presentations, firstly myself and then Arnie, and then after that we'll have a sort of open forum for Q&A and discussion. So yeah, any questions in the chat, please, and then at the end also feel free to raise your hand via the function in Zoom and unmute, and you can ask us a question directly. Brilliant. I'm going to share my slides now. Annie, can you see my slides right?
Yeah, that looks fine.
Great, thank you. Okay, so yeah, as I said, I'm still young from the Marine Energy Test Area. And this is a collaborative talk between ourselves and MEECE. I'm going to present first on Meta. But firstly, I wanted to touch on sort of wider sector in Wales to kind of set the scene. So before diving into at-sea testing. So in terms of tidal stream, Wales benefits from good resource in both the north and the south of the country, which you can see on the map. Comparative analysis suggests that over 1 gigawatt of tidal stream energy could be developed in Wales. Currently, development is focused around Anglesey in the north, where the 240 megawatt Morlais project is being developed. So far, 38 megawatts of that has been awarded contracts for difference. So things are moving forward there. Moving on to tidal range, over the years there and to this date, there's been a lot of interest in tidal range in Wales, since south and north coasts are home to the second and fifth largest tidal ranges in the world, respectively. So there's a lot of resource, and that resource is located near big population centers and industry, which is an advantage. And it's estimated that with the rollout of multiple large-scale projects in North and South Wales, tidal range could supply up to 9 gigawatts of electricity. Yeah, then there's floating wind development in the Celtic Sea. There are 3 test and demo projects being developed in Welsh waters, Erebus, Leo 1 and Leo 2. There's 2 1.5 gigawatt seabed leases that were awarded through the Crown Estate's round 5 leasing round, which just finished. And then one of those development areas wasn't leased, so there's a sort of another 1.5 gigawatts up for grabs in the current sort of leasing round. Then these are, just to kind of fully set the scene, these are the commercial projects currently in the pipeline in Wales. We won't go through all of these now, but you can see there's a strong pipeline of projects across fixed and floating wind, tidal stream and tidal range. There's not actually any wave energy projects on here, but there is good wave energy resource in the southwest of Wales. And we don't as marine energy wells, we don't do anything on fixed offshore wind, but there is already over 700 megawatts deployed and operational in North Wales, and then Owlin Moor, which is consented, and that would add a further 1 gigawatt, and then the Mona project, which is also consented, a further 1.5 gigawatts. So yeah, there's a fair bit in the pipeline. So that's the bigger picture. Um, Now to focus in on at-sea testing, which is an important part of de-risking the development of marine energy projects. And this is where the marine energy test area comes in. We've been operating for 4 years now. We offer the only pre-consented marine energy test sites in Wales, and provide an important stepping stone between tank testing and commercial deployment. At Meta, you can test tidal stream and wave energy converters. You can also test components for floating wind, and you can test most other infrastructure or equipment related to offshore renewables. Myself and there we go. Myself and Arnie will go through some of the past deployments that have happened at Meta throughout these presentations. So you can see the variety of things that have taken place. We're based in Southwest Wales in Pembrokeshire, and the sites are located in and around the Milford Haven Waterway. This is a map of the Milford Haven Waterway. The light blue water is is the waterway, and it's a big natural harbour. There are 8 Meta test sites in total, and these are split into quayside and open water. You've got our 5 quayside sites, which are all associated with Pembroke Port, and they provide easy access, low risk areas for testing. Each site is accessible via existing port infrastructure, so easy to deploy and easy to retrieve and monitor your tests. There's not much resource at these sites, but they're good for dip testing, component testing, material testing, or any other test that needs quayside infrastructure for support equipment. Then we have 3 open water sites, which offer more representative environments. They've got good wave or tidal resource, good depth, and seabed conditions for testing, but they're still close to port facilities. Warrior Way is our tidal stream site with peak tidal flows around 1.5 meters a second and water depths up to 20 meters. Dale Roads is our scale wave energy site with maximum significant wave height around 3 meters and 12-meter water depth. And then East Pickard Bay is our full-scale wave energy site, which has direct exposure to the Celtic Sea and Atlantic Ocean and depths up to 30 meters. None of the sites are grid connected. So although you can produce power, this has to be consumed on board the device or via dumped some way, maybe on a buoy or platform nearby. These are our site users. So we've got technology developers looking to test and validate novel devices and components. Research organizations supporting marine energy technology projects and conducting their own at-sea research. Supply chain companies looking to test solutions, such as new coatings, deployment methods, scientific instruments, etc. And these logos represent some of the companies that have used the Meta facility. One of the key advantages of using Meta is the proximity of world-class port and engineering facilities, as well as smaller boatyards. There is everything required to design, build, deploy, maintain, and recover a device. I won't go through the whole list on the screen, but you can see some of that. Yeah, so overall, the key benefits of testing at Meta are we've got all the environmental consents and leases in place for testing a wide range of technologies. We've got a large site data catalog, so both of these things save you the time and cost of developing your own site. There's a lot of local facilities and services which I've just been through, and then we have an experienced team that can support with test planning, and then there's also technical support from Catapult and the Welsh universities for people using the meta test sites. Okay, so now I'm going to go through 4 past deployments before concluding on some general lessons learned and opportunities for future collaborations. Case study 1 is Swansea University's tidal turbine. This was the first tidal energy converter tested at Meta in spring 2023, and then it was tested again in spring 2024. It's a 3-meter diameter horizontal axis turbine with a water pump power takeoff. And the aims of these test programs were to show that water pumping is a viable solution as a power takeoff for turbines with power and rotational speed um, less than adequate for widely available electrical machines. To show that standard blade design coupled with wet running bearings has a good cut-in speed and energy generation in low flows. To prove that local supply chains and smaller boatyards and low-cost operations are possible for a small-scale community turbine. And to collect multiple measurements of tidal flow data in a small proximity for future analysis. So the platform itself, which I'll show you in a minute, was developed with a local supplier, and this test program itself achieved TRL5, so technology validated in a relevant environment. There is a reference and a link to a published paper on this test program on the slide. And as it was a community turbine, the design is open source. If anyone would like to replicate it, and he can put you in touch with Professor Ian Masters, who led this research. If you'd like to find out more. So I'll play a short video now. Hopefully this works. So this turbine and platform is now on site again for another test program, testing CGen Engineering's next generation electrical power takeoff. So we're hosting a technology demo day with CGen on Tuesday, the 14th of October, to visit the device and see some of the operational data. If this is of interest to anyone, please get in touch and we can send you an invite. And this video just gives a bit more of a live shot of our tidal site. It's an estuary site, which means that doesn't really suffer from waves, and this kind of allows for access, 365 days a year, because you're not really, you don't really get weathered off so much in this environment, but it's still good real world tidal flows. Sorry, next slide. Yeah, this is a picture of the platform. It has a hydraulic arm to lift turbines in and out of the water, remote power, and a swinging mooring. It's a versatile asset that can be used for a whole range of different devices and modified in different ways. So that's available locally. So coming on to case study 2. The platform that we just looked at was also used by a company called Porpoise Power to test their oscillating hydrofoil tidal energy converter earlier this year. So as we know, traditional tidal turbines rely on rotating turbines like underwater wind turbines, and there are lots of successful examples of these. However, these turbines have very site-specific requirements. They need reasonably fast flows, need deep sites to avoid surface effects and seabed turbulence, and to accommodate large diameter blades. So Porpoise Power are looking at an alternative solution where they produced a hydrofoil that emulates swimming motions of dolphins and porpoises with wing-like foils that oscillate in tidal currents to generate lift. This oscillatory movement allows deployment in shallow water, more turbulent waters, as well as slower flowing areas, potentially expanding viable site options, potentially sites closer to shore, reducing operations and maintenance costs, and potentially lower flow sites which aren't accessible by existing turbines. So this technology really aims to complement existing turbine technologies, and there's clearly a place for both. There's a short film that's shown in a second. So yeah, it's a novel approach. What they managed to achieve at Meta was to deploy a 2.5 meter prototype in a real world flow with real turbulence. This real world deployment allowed them to validate and improve their models. And one of the most important things they gained was real world deployment experience, including installation process and marine operations. And this experience to them was key to refining and improving future deployment strategies. Um, yeah, and here's a short video of the fin oscillating. Good. So we've seen some of the tidal stream deployments that have happened at Meta. The next couple of past deployments show the wider variety of activities possible. Firstly, we have Dolphin Hydrogen, who used one of our quayside sites to demonstrate hydrogen production from seawater in a floating marine environment. And this was the first time this had been done in the UK. Um, Hopefully this video works. So this is Pembroke Port, where the Meta quayside sites are located. This is Criterion Jetty, which is the deepest and most exposed of the Meta quayside sites and was best suited for the Dolphin hydrogen deployment. The equipment, such as the electrolyzer, desalination plant, etc., were all off the shelf, but the combination of systems and operating them in the marine environment with newly developed processes was what was being tested and validated. Um, so testing at Meta allowed Dolphin to, understand interfaces between these key components, importantly, test effects of marine motion, um, and prove the end-to-end desalination and hydrogen production process. Um, their findings from this, they've entered into their feed for designing a system where they integrate hydrogen production on an offshore floating wind platform, which they aim to deploy in the Celtic Sea in the future. Yeah, the adjacent quayside facility, as you can see in the picture, very useful for the fit out of the barge, preliminary testing, and they used local supply chain for this. There you go. And then final case study is something different again. This is a Cardiff University research project which investigated low carbon concrete mixes for tidal range schemes, but also in other marine infrastructure projects. Globally, cement production accounts for 8% of CO2 emissions. Therefore, there's a lot of interest in low carbon concrete solutions. A tidal range lagoon will use a vast amount of concrete, as will upcoming large scale port developments that are planned. So, is low carbon concrete an option for marine developments? These low carbon concrete mixes use industrial byproducts and waste as the cementous and aggregate material. And then these mixes were compared with traditional mixes. So 100 samples were deployed at a Meta quayside site in the intertidal zone, which is a very harsh environment as it's continuously subjected to wet and dry cycles. And then the aim was to compare lab data from Cardiff University's Jura lab with the real world experiment. It's a bit of a graph there about the compressive strength and comparing the lab and the real world experiment. And so preliminary results showed that low carbon concrete achieved a structural grade even when exposed to a marine environment. Interestingly, there was a slight reduction in strength compared to that achieved at lab conditions. And this is just one of the parameters they tested. So there's a full paper on the full results of this experiment coming soon from Dr. Ricardo Maddalena. True. Sure. So now for some lessons learned from conducting at-sea testing. Unfortunately, I can't go into the specific technology developers' lessons learned, as it's not my place to share these. However, I can share some general lessons learned which apply to at-sea testing. And this isn't an exhaustive list by any means. So building something for the first time usually takes longer than expected. Something that often crops up are supply chain delays for single orders or um, specialist services. And then even once you have all the everything working and ready to go, bad weather can delay proceedings. So it's important to build in loss of contingency into an at-sea test program. Um, Next one is that some early stage technology developers and researchers are less experienced working in the marine environment, and Meta and MEECE and an experienced local supply chain, therefore even more useful to help support these test programs to ensure they are completed safely and successfully. Related to this experience, small scale at sea testing is key for early stage developers to gain experience in risk management and deployment strategies. This, can then be incorporated into future designs. Developers learn a lot about the deployability and recoverability of their device and how this can be done better next time. And these findings can be of equal importance to performance testing data. The marine environment is extreme and equipment can break or become compromised. Compromised devices are subjected to biofouling, corrosion, abrasion, wave loading, sedimentation, burial. This can obviously be mitigated in the design phase, a robust monitoring and maintenance plan, but it's also important to have contingency plans in place and insurance in place, and sometimes a decommissioning bond may be required, so test assets aren't abandoned at sea. And then the next one is it is expensive to test at sea, so make time in the water count. For example, do robust dry testing is it's much easier to fix something onshore than offshore. Also ensure robust methods and systems for data collection are in place. If you don't collect the data because sensor wasn't working, then you will all that effort for nothing. And then finally, there's a lot of paperwork associated with these projects, in terms of marine licenses and leases from various different regulatory authorities. So luckily, Meta takes care of this, but it's important to be realistic about the timeframes in gaining approval. You can't just turn up to Meta the day before and expect to go in the water. There's some processes to go through. Sorry, I missed that point on there. There we go. Finally, I'm going to finish. This is my last slide on some thoughts on how academics can collaborate with Meta and/or our site users for mutual benefit. Firstly, there may be some opportunities to support Meta site users with modeling and the theoretical side of their technology development. We have a large site data catalog of marine energy or marine environmental and physical data. So that's available to researchers as well. We have the multi-purpose test barge, as I showed you in case studies 1 and 2, which is available to be used at Meta or nationally. There's the turbine, Swansea University tidal turbine and drivetrain, etc., is all available to be incorporated into other projects as well as it was with the CGen project. Then if anyone is developing innovative survey methods, these can also be tested at Meta, and we're keen to support the sort of testing in any way. And we've got baseline data you can compare against. We're interested in developing collaborative research funding bids where at-sea testing is required. And we're available for site visits and demo days to help with knowledge exchange within and between disciplines. The next one is on the 14th of October, as I mentioned. And then finally, for those testing at Meta, you gain complimentary membership of Marine Energy Wales, which gives you access to a network of over 100 members. So that's a few ways to get involved. Brilliant. Thank you very much for listening, and happy to take any questions after the next presentation. Get over to you, Annie.
Thank you, Sol.
I'll just stop sharing.
Yeah, please, if you can, then I can share my screen. Yes, good afternoon, everyone. So pleasure to see a good turnout. I need to figure out how to use this platform. There we go. And what is here? Cool. Yeah, so I'm Arne Vogler. I'm from the Offshore Renewable Energy Catapult, based in Pembroke Dock, or working from Milford Haven most of the time. You know the topic of the talk, and I think I'll just jump right into it and tell you to start with a little bit about the catapults in case you are not so familiar with them. And how do I get rid of this symbol? I don't. Okay, it doesn't matter. So catapults, there are a total of 9 different catapults in the UK. These are organizations founded or set in place by the UK government with the aim to provide support to UK businesses, grow the economy in a range of different contexts and situations. That is the map on the right-hand side with a very small print where it tells you the different types of catapults, including connected places, energy systems, satellite applications, and others. So we are the Offshore Renewable Energy Catapult, as the name suggests, focused on the development of energy from the ocean. And over the recent years, the focus has certainly very strongly shifted towards offshore wind in the Welsh context, particularly offshore floating wind. Even though there are now discussions how deep can we go with fixed foundations, there's a lot of interesting work to be done. So as the Offshore Renewable Energy Catapult, the vision is to work towards a thriving net zero UK that is powered by renewable energy. And we do this by working together with businesses of all sizes. So it could be individual entrepreneurs, inventors, small and medium enterprises, but also up to large corporations or even multinational corporations to help them bring technology to the market, to demonstrate it, to validate it. We do this by making available our unique facilities. We have huge test facilities up in Blyth, Northumberland. Also recently opened up the facilities in Aberdeen. And now, over recent years, we developed more and more regional offices to provide support, basically, where it's best required. That includes an operations maintenance base in Grimsby. It includes our Marine Energy Engineering Center of Excellence down in Pembroke Dock, and a number of other outlets. We got an office down in Hale, down in Cornwall, with the site office in Plymouth. That by our work, some of my colleagues are working mainly on smart environmental and other interesting, important technology developments. So this whole point is it's twofold, basically. One is to grow the UK economy, bring in more money, generate jobs, and also work towards a reduction in carbon emissions, make sure we do have a world worth living in tomorrow. So in the Offshore Renewable Energy Catapult, we have around about 320 staff, a lot of them trained engineers of various disciplines. We got a lot of people working on electrical issues, cabling, high voltage systems, but also then going down to robotics and lower voltage, different application systems in electrical context, electronics. But a lot of our work also is around hydrodynamics, aerodynamics, marine operations. And we do this through our regional centers, 8 of those. You can see the locations, and we also have good collaborations with universities. We do have a very good connection with Plymouth University. I'm not quite sure why they're not listed here, actually. Maybe it's an old slide. But we certainly, this is not an inclusive list. The academic research hubs, we are certainly very well connected with loads of different universities, including Bangor and Swansea and Cardiff in Wales, but others around the whole piece, really. So the mission that we have, the vision, we try to achieve that by providing testing and validation services. So if somebody has a tidal turbine or energy generator and they say, this is what it can do, then that's great. But it's not good enough for any investors to throw money at somebody. So it needs to be tested and validated. We need to build up credibility, confidence, so investors can really say, this is great, I'm going to back this. So that needs a testing and validation program. A lot of that traditionally has been done in Blyth, where we have a full ISO certified test labs and can work to the very high standards. And we are now working more and more towards having these services available in the field as well. That would include the meta test site, where, of course, testing of marine assets, you can do so much as you go through the TRL ladder in a controlled environment, but at some point it's just absolutely essential to go out into the wild where it's a non-controlled environment, but we still need to test and validate. So we do have a considerable engineering expertise, huge office in Glasgow, and then small engineering team, for example, in Pembroke Dock. That's the team I'm leading here, with a good combination of civils engineers, coastal engineer, mechanical, electronics, energy engineering, ocean engineering. So it's quite versatile, which makes it really interesting to work at, I must say. So there's a lot of research development going on. And as we go along, we try certainly to provide opportunities, train opportunities for the supply chain. That was one of the reasons we came down here with MEECE to Pembroke Dock to help the supply chain to adapt and grow into the renewable sector. Traditionally, we do have a very huge petrochemical industry here. It's the UK's biggest leading energy port, the port of Milford Haven, with most of the oil and gas imports coming through the waterway. So we got a lot of expertise here in engineering terms and infrastructure, but in a different field. So we need to adapt to, well, to go green, basically. So how do we do these things? Thought leadership. So we work closely with politicians and decision makers, policy makers, and providing them with the information that they require to come to a decision, to decide, okay, this is the way to go. This sounds all credible. We identify priorities, what is more important than the others. So at the moment, we can clearly see there's a big drive towards wind, offshore wind in deeper water, which means there's a reduced drive then in pushing for wave energy or tidal energy. Where initially, when I came down here 6 years ago from the northwest of Scotland, the Outer Hebrides, there was a very strong drive towards wave power development in Pembrokeshire. There still is that ambition to do, but if you identify priorities and look at economic growth and opportunities in terms of energy security, then offshore wind is the way to go. I say that a little bit with a heavy heart because I'm very passionate about wave power and tidal power, but we need to take the opportunities where they come along. So we do provide industry leadership, but as this fronting up, and that is something Marine Energy Wales, of course, the governing body of Meta, is doing as well. So by providing a network of like-minded people with the leadership to then lobby out to politicians to make sure that we are going in the right direction. And of course, very important, if you're a small company of any smallish size, then quite often the world can be overwhelming. It's very difficult to identify where can I get funding, how do I take the next step. So we do provide a lot of support to SMEs, smaller businesses, to help them grow again and increase the service offering. These are our focus areas. I think I've mentioned them, most of them already, possibly. So is smart operations maintenance, something we are very interested in. Marine energy still is out there, and we are still working hard on it. Floating wind, turbine development, improving blades. We are talking about bigger and bigger wind turbines. Not so long ago, 10, 15 years ago, people said the biggest wind turbine you can go for is 5 megawatt. Now we're talking about 20 megawatt and bigger. So there's a lot of engineering effort required. Just reminded myself, I'm not here to talk about the catapult. I think the topic of the day is something else, so I try to get there. So down here with me is Marine Energy Engineering Center of Excellence based in Pembroke Dock and working very closely with the local supply chain, local organizations to deliver services to help them to grow. And part of what we're doing is the testing and demonstration of prototypes and also of individual components, any supplementary systems or survey methodologies. And a lot of that we are doing at the Marine Energy Test Area in short matter. And I guess that's why I'm here today. I'll now showcase a number of case studies that we've been through since we launched operations here. So active operations commenced around about 2020, 5 years ago, 5.5 years ago. And that happened in parallel with the setting up of Meta. So when I moved down here, Meta was way more than a concept. It was getting very close to operational, but there was still more consents and another consent and another piece of paper required. It's a very, very tedious process. which is one of the reasons why it's very good to have these pre-consented sites so developers can focus on what they can do best. So the first operational project that we started here was to set up a test asset, basically with the idea of using a versatile test platform that we can then use similar to the floating barge that Meta already presented on. But we're looking after for a platform that we can use to demonstrate support a number of projects. As it happened, we're very lucky really to work fully within a circular economy context by recycling a lot of equipment. So initially it started that Marine Power Systems, MPS, they had approached us and they said, okay, we've just finished a test program down south in the English Channel with the wave energy converter, and they had this power buoy that they used for data acquisition and for power management, which was now redundant. So a lot of people know marine assets can very quickly turn into marine liabilities. So once they've served their initially useful purpose, they need to be taken care of somehow. Either they need to repurposed or whatever it is. In any case, this buoy was available. It was basically gifted to us by Marine Power Systems, where they said, well, if you want it, you can have it. And you see it on the left bottom pictures there as we took it on and then transported it from Falmouth by lorry over to Pembroke Dock, propped it up at Mainstay Marine. Or initially, it was parked up at Williams Shipping, but then got it over to Mainstay Marine, came up with a full specification, identified requirements, potential requirements for new projects, and worked on the proper mooring solution that was required. The idea for this buoy we had was to use it for the wave energy test sites. So that is the Dale Roadside and East Pickard Bay. And we had a number of interested parties lined up very quickly that were very keen to have their systems installed in this context. So talking about circular economy, when it came to the mooring system, for example, that again we managed to repurpose. We had a wave power company testing device here in the Milford Haven waterway some years ago, before Meta or Catapult came here. That was Wavetricity. And there was still the old mooring spread and the anchors that they had used for their system. So we managed to take this as well. And it was a nice, it felt good, I must say, just to not uh, throw more energy to production of steel to get all these things organized, but just to recycle something. And you can see it's a nice bright color. Wednesday did a fantastic job in coating it and fitting it out with the control system. On the control system, that was a nice first part of a collaboration that I was part of with Swansea University, where they were a leading partner in the Selkie project, cross-Irish Sea collaboration with a fair few Irish partners. And part of their objectives was to develop a data acquisition system that using some encryption for data security. And they basically needed a system to showcase what they can do. And I said, well, I need a system to do exactly this. Let's team up, let's work together. So big thanks to Tom Lake and Ian Masters, who were very helpful helping us out to get everything together, because otherwise we would have struggled. I guess we would have been able to do something, but it's just the manpower and the effort required. And that's one of the advantages of this area. People are work together very nicely. It's very easy to collaborate. So there's a less competitive spirit. I think there's a lot of team spirit out here, which is really nice to be a part of. So this now was our first meta deployment. In fact, it was the first meta deployment. And I think when we deployed, not even all licenses were fully in place. We worked very closely with the Milford Haven Port Authority, a connection that was managed through Seoul, to make sure everything is compliant with all legal requirements and we're not upsetting anybody at the regulators. So there are, of course, ways for port authorities to deploy systems under mooring licenses and scientific exemptions. And so in any case, all these things I did not need to worry because we had Meta to take all this burden off my shoulders. And that allowed me to focus on the technology, which was very good. So it brings me to the first real project. This was just a setting up project to facilitate other activities, of course. So this was working with a company called Intelligent Mooring Systems, and their product is a system to reduce the shock peak forces in a mooring system in serious severe wave conditions. So you got a big storm, every so often you get a wave breaking against your structure or whatever, imposing very strong, very aggressive forces to a system. And your mooring system, of course, must be designed to absorb those forces to cope with them, meaning that most mooring systems are utterly overspecified. If you look at the average conditions or summer conditions, because these things must be able to withstand other situations as well. So we had this mooring damping system installed. Of course, was quite critical to have a system that is fail-safe. So we had to build in some redundancy in case a novel prototype not widely tested. We need to have some bypass system in there, which worked was there very well. It wasn't required actually because the system did not totally fail. There were some issues, of course, some challenges, as you always expect to encounter. Otherwise, there would be no need for this testing. So we started up doing some bench testing with the system in Falmouth at the DMARC site, where they got a test rig for dry testing of similar systems. Also did some Orcaflex modeling, numerical simulations to find out what we expect. Then installed the system at sea. What you can see here is some ROV footage of the system. And then we had a number of load shackles in there just to measure the forces in the system. And that included testing without and with this damper system included. So we have something to compare against. And all in all, quite successful, certainly from our side, and to find out that we can do these kind of tests. And I think everybody was quite happy. Similarly, around the same time, we had this case study or this test program with a company called Hexagon, who have developed a paint inhibitor to minimize corrosion or reduce corrosion in marine applications. And the way to test their product was to have this panel installed on the buoy, just slightly above the splash zone, or you could say within the splash zone. Those panels were coated with different paint systems, including the primer, including the top coat, and it was kind of a blind marking, you could say, or was it? In any case, we just mounted all these panels in a certain pattern, and we had, of course, noted down which coating was on which panel. Then to stimulate corrosion, we put in scratches in each of these panels. So if you've got a perfect top coat, then you can wait a long time. So we wanted to accelerate the deterioration process. So we scratched them, we annoyed them a little bit, had it out installed for 250 days, and then recovered the system again, dismantled, and sent it in for a lab analysis. And the results were very, very successful for Hexagon. And they now had the scientific evidence and the clear proof, you can say, that their system indeed works very, very well and outperforms most, if not all, of the competitive products. Certainly of all of the products that we tested on the market. So very happy client, and we were very happy, and it worked very well. Also on the same test asset, the MEECE buoy, we had the Graph Marine project. They had developed an energy deck system. So this is a modularized solar system with the idea to mount this on deck space on huge ships, on big ships, container ships, tankers, and then to produce power to support the hotel load of these ships. So the onboard diesel generation can be reduced. Again, that was a very successful outcome. And the client have now moved on to do some more wider sea trials on ocean-going or sea-going vessels. So they moved on from the test site fully to the real world. But in this case, we had this self-contained system on a small frame mounted on our control cabinet, and then with a communication system utilizing 4G comms network. And again, the system worked very, very well, has provided very important background information for the client. Same site, next test them, but without our test buoy this case. So this was a company, Tidal Anchors. They have developed a bidirectional novel anchor solution that works very well in tidal energy systems where you got the flow changing direction by 180 degrees or thereabouts every few hours, which is a challenge for traditional anchors because they need to make sure that they bury in every time that you pull from a different direction. So they had this novel solution and went through some initial testing, some computer simulations. But the first test we did with them was some beach testing, so a semi-controlled environment onshore, comparing against different anchor solutions. But that wasn't good enough. We then followed up in an at-sea testing at the Dale Road test site, where we had a range of different anchors compared against the tidal anchor solution. Then we monitored everything where we had load cells integrated in the mooring line, so we could measure exactly the pull forces and finding out how much load they can take before breaking free. And then we also had some interesting findings with the wildlife in the area, which is, of course, always nice to see. So this crab was particularly interested. We also had some fish having a look, but this guy he really was keen. He really liked this new anchor. And at the bottom right picture, you see the team in Swansea Beach. Again, that's where we work closely with Swansea University. They are very lucky to own that beach. It's a nice thing. I would love I could own a beach, but I don't. But so that was very easy then to test there. Again, content-wise, it was very light for us to test at Swansea Uni, but then we can move on to the meta test site, and that was perfect for us. Next project, again, Dale Rose test site, more focused on the biology. So the idea here was the underlying idea of our client was to create an underwater garden, have a carbon capture system basically by stimulate wildlife, stimulate aquaculture in the water column. And initially they were talking about some polyprop lines. We worked with them and said, look, the idea of throwing plastic in the water isn't really so great. Can we do something else and maybe use some natural fibers? And that resulted in this test program where we compared lines hemp sisal jute with polypropylene to find out what has the best growing properties, what works best. We had them moored side by side, 12 different systems, so three of each type in slightly different configurations, and then we pulled everything out every few months to explore, investigate. We are not marine biologists in the Catapult, so when we need external advice and the competence, we pull it in. So we had a local marine biologist leading on the analysis because, of course, the moment you pull something out of the water aligned with biofouling, things start to die or to fall off. So it's a very careful process, and if we don't feel we have the competence in-house, we find someone else who does and get them on board to help with the job. This is a project out at the East Pickup Bay test site. Um, Fairly ambitious. This was about an 18 month, initially talking about 2 year deployment of huge concrete structures. And that's for a company called Exo Engineering. So Exo Engineering, a company looking at nature-based solutions to work with or build eco reefs using low carbon concrete. And they talk about this nature-based engineering, nature-inclusive design. So having some structures that attract basically wildlife. And one application for this would be scour protection in the offshore wind systems, or just use them as artificial reef or use them for coastal protection. So we had a range of different structures installed in, I think, 20 to 30 meter water depth, then monitored regularly. The test instance also included this bundle of just standard natural rocks, more as a baseline system to compare against, and then all sorts of different types. This program was monitored, supplemented with some monitoring using underwater cameras and eDNA samples, other tests. And then after 18 months, we recovered everything again. So that was good as well. Another project, better move forward here. We're running out of time, I guess. That's with Ocean OS and Pebble. So companies very active in the market, small companies. Pebble have invented, developed their own monitoring systems, including underwater camera and turbidity meter and systems to measure properties of salt water. Working together with Ocean OS company, they are more interested in the data side. So using novel communications methods to get data from the seabed to the surface and then broadcast that to a shore station and apply machine learning AI algorithms. So in this context, we also deployed hydrophones, ADCPs, and try to find out the balance basically between shipping noise, for example, anthropogenic noise against nature-based noise. So we logged all the AIS shipping movements over that period of time to find out the noise, the sound that we measured. How does it compare, or any waves or any wind? How does it compare against the um, or what is it? Where is it from? Is it man-made, or is it coming from some other sources? And then in addition, a range of other experiments. I wouldn't call them experiments, data acquisition activities. So currently we have a expand radar system, hydrographic expand radar system installed at St. Anset. Not quite overseeing the meta sites. Could probably tune it to get a glimpse of East Picard Bay, but more looking the input parameters, what comes in there, so we can measure waves and currents to some degree with the system. We do have ADCPs, we do have wave buoys, sonar systems. There's a wide range of equipment available at the site, and if funding allows, we can pull in additional resource um, from our partner universities, or possibly through a funding project, uh, get new systems into the area. So now a few words about the benefits and challenges of testing at an open water or more sheltered water test site. So benefits, of course, if you go to a site where you've got an established infrastructure and a pre-consented test area, you can expect to receive a lot of logistical support. That's not just directly from the test site operator, but the test site operator, they will know what other contractors are available in the area. They will also know who has delivered well on previous projects. So there are lessons learned that people don't need to repeat. If you know that some contractors are very, very good, very trustworthy, reliable, others are not so great, then it's great to know somebody, to have somebody that points you towards the right direction. All consenting issues dealt with by the operator, that's a huge help because this consenting can be a massive burden. And if small companies try to just get their head around the whole marine operations or even the whole marine technology, then you really want to focus on that. You can see a lot of companies working in wave or tidal energy, they got massive teams dealing with consenting. And if you look, I always was frustrated as an engineer looking at the ratio between environmental consultants, marine biologists, and engineers and engineering technology development companies. But it's required to have all those people on board because otherwise you will never get the consent. So if you're early stage technology provider, to have somebody that has all the consents in place is a massive help. And then, of course, there's existing baseline data, so we know what we are measuring against. And a really key point really is the support from a test set operator, or in our case, I would say the support from MEECE Catapult as well, in addition. So this whole team, Meta and MEECE works really well together. So we can make sure that our clients can focus on what they should be focusing on, and we can help them to, yeah, not fall into certain traps that a lot of people have fallen. There's basic things like galvanic corrosion, the wrong materials bolted together, or misunderstanding, lack of understanding of the aggressiveness of salt water, all sorts of things. And we are fairly experienced in marine operations and dealing with those challenges. So the practical challenges of a marine energy test site, of course, it's not a controlled environment, but that's what makes it attractive at the same time. So it's a challenge, but it's not necessarily a negative. Um, to set something up, to prepare something, wait for the right weather, sometimes needs quayside space for quite some time to have everything ready in place. So that needs good access, good interaction with the port authority or the owner operator of a quayside. That's a definite given down here. Pembroke Port, Milford Haven Port Authority, they are very supportive, very keen. Big challenge is the weather, of course. So that's something we can do very little about. But having come down from the Outer Hebrides in Scotland, I can say that weather is much less of a risk and threat down in Pembrokeshire than it was in my previous home. So, yeah, the weather is easier to deal with down here, I guess, but still it's a very important consideration. And going out onto the wave power test sites, of course, it needs to be taken care of. Operational limitations, yeah, distance to client base is a bit of a challenge if people they might come from somewhere in the northeast of England. But that's the same everywhere, I guess. And costs, yeah, of course. Meta needs to live as well, so there's some money involved, some payment. But generally, it's possible. Try to find some funding programs to support the companies with that. And I think I covered all these advantages of using a pre-consented sites multiple times now. Um, so the experience of a real world challenge to get stuff into the real world, into the sea, is invaluable for any developer. You will learn so much from doing that. The access to the wide range of universities and other companies here is great. And it's imperative to go up the TRL ladder. We need some real world testing. It's not an optional choice, it's mandatory. It's the proof of the pudding. It's got to be done. And that's the end of my slides. And sorry, I didn't leave too much time for questions, but that's how do I run?
Thank you, Annie. That's super. Thank you very much. There is a question here for you. It says, it's from Ali Price from Area What Uni? Is your MEECE test buoy for measuring wave elevation, or does it have a power takeoff i.e., is it a test wec? Can you clear that one up, please?
Yes, no, thanks for the question, Ali. And no, it's not a wave energy converter. It's not a wave measurement system. It's a floating platform to facilitate testing of all sorts of things. So if somebody wants to put on a power takeoff, probably would have to be something hinged on it, or we could put something below. That is possible. We can explore this. We do have IMUs on the 6 degree of freedom accelerometer-based systems that give us the motion of the buoy, which would allow us to measure waves. But because of the dimensions of the buoy, so 4 meter diameter, 9 ton of weight, there are limitations of how good you can measure waves. For big ocean swell waves, you get some results. If you want to capture smaller wind waves, then you need some smaller buoy. But we do have some of those as well. Our test buoy itself is not a key purpose is not to produce power, nor is it to measure waves.
Thank you. And then there's another question, which is what kinds of routine environmental monitoring is conducted or has been conducted at the test sites, i.e. acoustic monitoring, sonar imaging, or biofiling? Thank you. Yeah, so thanks for the question. There's been a lot of work done on the tidal characterization, lots of ADCP deployments. So they give good point measurements within the sites, and we're interested in getting more of a spatial coverage. So maybe some vessel-mounted ADCP deployments at some point would be good. We've got lots of wave energy data, and there's a live wave buoy at the East Pickard Bay test site, which you can access the data via our website. There's been multiple, 2 rounds of bathymetry mapping, multi-beam bathymetry, and then and then in terms of the sonar or acoustic monitoring, what the main bits is what Arnie's touched on with the Pebble project with the passive acoustic monitoring then, and I know that Arnie got more projects to well out in the Celtic Sea now to map the soundscape in the Celtic Sea. So there's been a little bit, but not loads of acoustic monitoring so far, but more to come. And then there's another question here. From Sergio, do you also do any kind of fatigue testing for wave and or tidal devices? Arnie, can you take
I
that one,
can take
please?
that, sure. We haven't done that at the meta site yet because it wasn't required. The question wasn't asked, but it's something we can certainly do. Would be very happy to do. So depends on the level of detail that is required. There are different ways of doing it, including sending equipment down to a lab analysis or testing to failure, um, having something installed for a certain period of time, and then put it into a lab, compare it against some other novel piece that hasn't been installed, and go through various cycles. It's something we can do, but we haven't done it Meta yet.
Thanks, Arnie. I think it's time for the last question. Are there any resources available to see the history of wave and tidal devices tested at these sites? So yes, there's a past deployments page on the Meta website. I'll put a link in the chat now, and that gives you all the devices deployed to date, and you can read up on them at your leisure. And if there's any more detailed information, please just get in touch directly. Thank you. Okay, so if there are no further questions, I think we'll wrap up now. Thank you, Arnie, for presenting. That was great. Thank you, SuperGen, for the opportunity to speak, and thank you to everybody in attendance and listening and participating in the session. And if you've got anything else, please just get in touch directly with us. We're happy to pick up the conversation. Thank you. All the best. Bye bye.
Thank you. Thank you for sharing, so.
Cheers.